Volumes of revolution, the disk method. We will focus on rotating about horizontal lines of the form y equals a, or with respect to x. Objectives. By the end of this lesson, you should be able to identify the region being rotated, ensure the axis of rotation is a horizontal line y equals a, find the limits of integration that need to be x values, and set up the integrals with respect to x needed to find the volume of the solid. I want to begin by having you try to imagine rotating this shaded region around the x-axis. Try to visualize what this three-dimensional solid looks like. So the region I'm talking about is the one bounded here on the x-axis between 0 and 2, and it's bounded by the curve y equals x squared. So what you're thinking about doing is taking this region that's bordered by the x-axis, this curve, and the line x equals 2, and imagine rotating it around the x-axis. So imagine this region coming out at 2 and then going all the way around and then meeting itself back again. So try to imagine what this solid is going to look like. So is this the figure that you imagined? So I want you to notice that the shape of the cross-section is a circle. So here was that region that was bound between 0 and 2 underneath y equals x squared, bound by the x-axis and x equals 2, and rotating it around the x-axis, we end up with kind of maybe this horn-looking shape. And you can see that if I choose some random x value to draw a cross-section or slice through to get a cross-section, my cross-section is a circle. Now let's go ahead and remind ourselves the area formula for a circle. So the area of a circle is pi times the radius squared. So we're interested in finding the volume of objects obtained by taking regions and rotating them about different lines. So we're going to start by rotating them around horizontal lines, first around just the x-axis, and then we're going to move what's called the axis of rotation to different horizontal lines of the form y equals a. So now let's formalize this idea of finding the volume of a solid of revolution. This is called the disk method, and we're going to take our cross sections to be perpendicular to the x-axis. So to do this, we need a function f of x that's continuous, and we need f of x to be greater than or equal to 0. So we need the function to either be above the x-axis or equal to the x-axis on the interval from a to b, the part of the graph that we're concerned with. Then the volume obtained by rotating the region under the graph about the x-axis, so instead of using the word around, we use the word about, is the following. So we aren't doing anything different than volumes with known cross-sections. So I'm going to go over how we're getting this formula that we're going to be using. We should already know this formula here. This is the formula for volume of a known cross-section. So we're extending from x equals a to x equals b, and we want to put our general area formula into the integrand as a function of x, so a of x. Well, the area of a circle, because we said our cross-sections are circles, is pi times the radius squared. But the radius needs to be a function of x. So pi times r of x as a quantity squared. So I need to rewrite the radius as a function of x. Well, this constant pi can be taken out of the integral to take us up to the second column, this next line. So we have pi times the integral from a to b of the radius as a function of x squared. But the radius can be found by doing top minus bottom. So taking it down to these images below, and sorry, they do look a little bit blurry here. So here is an individual cross section. So here's my circle, and here's this, generic x that we chose to draw a cross section at. And we're interested in the radius. So the radius is right here, so it could be thought of as top minus bottom. And the top function here, this is the function f of x. And the bottom of the radius, well, it stops right along the x-axis, which has a function of y equals 0. So top minus bottom is f of x minus 0. So my formula that I'm going to use is pi times the integral from a to b of just f of x squared dx, because we never really write this minus 0. So that's the formula we're going to be using to find the volume of a solid of revolution. So we're going to be typically leaving the pi on the outside, and then setting up our integral from a to b, those limits of integration from along the x-axis, and then top minus bottom. So if the bottom function is the x-axis, the x-axis is y equals 0 as a function, so that's why the bottom function is merely 0. But we'll see an example of the bottom function being a different function than y equals 0, and that changes things just a bit. So r of x is the radius of the circular cross-section at different values of x. So this is really sort of a special case of areas with known cross-sections. Alright, let's take a look at our first example. So calculate the volume V of the solid obtained by rotating the region under y equals x squared about the x-axis for x between 0 and 2. So let's go ahead and draw a picture of what's happening here. So I'm concerned for only x values between 0 and 2. And I want to rotate the region under y equals x squared. So y equals x squared only between 0 and 2 looks something like this. And I only care about what's happening right in between these two x values. So I'm concerned with rotating this region here. So this is the region that I'm going to rotate around the x-axis. So some of the things I want you to get in the habit of doing. For one is definitely drawing your graph, labeling your graph. So here's y equals x squared. I'm making sure to mark important values like the limits of integration. These x values extend from 0 to 2. And also marking the axis of rotation. So whatever line we are rotating around, we usually use this little symbol to indicate that's the line we're rotating around so we don't forget. So now our volume formula is pi times the integral from x equals a to x equals b, or x equals 0 to x equals 2. So now in general, what needs to go right here is the radius as a function of x, and that quantity needs to be squared, the radius squared. So I'm going to need to add the radius in here and square that quantity, dx. So each of my circles, I'm going to draw a cross section here. So if I were to rotate this around, let me just pick some random x. If I were to rotate it, here's one of my cross sections. Here's one of my circles. So my radius here is this region, or this height, which is top minus bottom, which is just the function y equals x squared. So top minus bottom is x squared minus 0, because the bottom of the radius stops right along the x-axis, which is y equals 0. So what goes right here is x squared. So technically x squared minus 0, but we're not going to write out subtracting 0. So when I stop at the x-axis, I don't need to worry about writing the bottom function, which is just 0. So now I am going to go ahead and simplify it. And this section 2 is about setting up the integral more than anything. We're typically allowed to use our calculator to solve these types of problems, although this one's very basic. But I do want to go over simplifying. We can write this as pi times the integral from 0 to 2 of x to the 4th dx. So just a quick reminder, these two exponents get multiplied. So I'm applying the rule. If I have x to the m times n, that's x to the mn. So these two are multiplied. It could seem like they're added because 2 plus 2 is also 4, but I just want to clarify that these two are multiplied. And then I don't want to forget the pi in the front. So this is the formula needed to find the volume. We would need to calculate it all the way, either by hand or with our calculator. But the setup is the most important part at this point. So this sets up how to find the volume of this solid of revolution. Alright, this next example, calculate the volume V of the solid obtained by rotating the region bound by y equals x, y equals 4 minus x, and the x-axis about the x-axis. So we want the region bound by y equals x, y equals 4 minus x, and the x-axis. So let's go ahead and sketch this out. So y equals x, looks like this. So it has a y-intercept of 0, a slope of 1. So this is the graph of y equals x. Then we're going to have to graph 4 minus x. So 4 is the y-intercept. And I have a slope of negative 1. So I'm going to have to go down 1 over 1, down 1 over 1. So I know that I'm going to end up getting to positive 4 on the x-axis. So I'm going to go ahead and now sketch that line. And it would keep going. So this here is the line y equals 4 minus x. And I'm bound by the x-axis. So that's already been drawn for me here. So the region that I'm talking about, the region of intersection of all three of those, is this triangle shape right here. So this is the region that I'm going to rotate about the x-axis. So the intersection of y equals x, 4 minus x, and the x-axis, the part they all have in common is this triangle, and I want to rotate that around the x-axis. So now, what I need to think about is top minus bottom. So that's going to tell me the radius. So remember, we're going to our formula here, which is pi times the integral from the values along the x-axis and then of top minus bottom, or the radius of my circle. But something unique happens in this problem. There is a different top and bottom function depending on where I'm at on the x-axis. So let's just say I chose some x1 here, and I chose to draw myself a little circle as my cross section. So here's my circular cross section. The top of this function is the line y equals x. The bottom is the line y equals 0. But if I were to choose, let's say, this point over here, x2, and if I were to draw a little circle as my cross section, well, now this height is a different function. So the top of this function is 4 minus x, and the bottom is still y equals 0. So what this means is that I need to split this integral into two separate integrals because there's a switching of the functions right at this point right here. So this point of intersection, is y equals 2. So we can set the two functions equal to each other, or if we were to be very careful when we were drawing 4 minus x, we'd go down 1 over 1, we go down 1 over 1 again. We'd see that they intersect at x equals 2. So we're going to have to split up our region at 2. So the first integral is going to be pi times the integral from x equals 0 to x equals 2 of top minus bottom over here between 0 and 2 is going to be just x. So x squared. And then we're going to need to add, doing it again, but going from 2 to 4 of the other functions. So x equals 2 to x equals 4. And then top minus bottom is 4 minus x. Quantity squared. And I forgot my dx's to be formal about it. So adding these two integrals together, this portion here is rotating. Let me do it in a different color. So this portion right here is rotating this triangular region, and then rotating this triangular region here is this portion. So then I'd want to make sure to add those two regions together, and that's going to give me the total volume of the solid obtained by rotating the entire region around the x-axis. So when I think about the radius, the top minus bottom, I have to make sure that throughout the interval from 0 to 4 that there's always the same top function and the same bottom function. If it ever switches, if the top switches, if the bottom switches, then I have to set up more than one integral to find the total volume. And for the final disk method example, we want to calculate the volume V of the solid obtained by rotating the region enclosed by 1 minus x squared and the line y equals negative 3 about the line y equals negative 3. So let's go ahead and sketch our region. So we have 1 minus x squared. So 1 is the y-intercept. And then we have, this is a quadratic that's facing downward because the leading coefficient is negative 1. So I'm going to have this downward facing parabola here. And it should be symmetrical. It's not perfect. So here's my downward facing parabola, and then the line y equals -3. So y equals -3 is a horizontal line at -3. So here's y equals -3. Here is y equals 1 minus x squared. So we want to rotate this region that's enclosed between these two graphs. So I'll try to highlight it in blue. So this is the region we're trying to rotate, and we're trying to rotate it around y equals -3. So my limits of integration are these points of intersection. So right here and right here, those are the x values I want to integrate from. So I need to find what this x value is here and what this x value is here that come from these points of intersection. So to do that, I need to set the functions equal to each other. So set 1 minus x squared equal to -3. So if I move everything to one side, I'm going to get 0 equals, and I'll get x squared if I add the x squared to the other side. And then if I subtract the 1, I'm going to get x squared minus 4 equals 0. So 0 equals x minus 2, x plus 2. So I end up getting x minus 2 equals 0 and x plus 2 equals 0. So x is plus or minus 2. So -2 and +2 are my limits of integration. So now let's start to set up our volume formula. We have pi times the integral from x equals -2 to x equals 2. All right, and so now what goes right here is my radius. So my radius needs to be a function of x, and that whole quantity is going to need to be squared. And then we're going to have dx. So let's try to draw one of our cross sections here. So I'm going to pick a different color and then draw my cross section. So at any different x value I choose, I need to find top minus bottom because that's going to be my radius. So I'm imagining this is the radius at this x value, so I'd have to go all the way around to draw my little circular cross section here. So the radius, top minus bottom, well, the top function is the parabola, so 1 minus x squared, the quadratic. So 1 minus x squared is top, minus the bottom function is -3. So I have 1 minus x squared minus -3, which we can simplify. So we can write it all out right here. 1 minus x squared minus -3. So this inside here is the radius of my cross section. So it's the radius of my circle. So found by doing top, this portion here, 1 minus x squared was the top, and then minus -3 was the bottom. So now I can do a little bit of simplifying. I can rewrite this as pi times the integral from -2 to 2. And then on the inside here, so if I minus a negative becomes a plus, so I can rewrite this as, this should have been a squared. So this should be 4 minus x squared squared dx. So this is going to be the setup to find the volume of revolution rotating this whole region around the line y equals -3. Just a couple things. So let's remember that this exponent does not distribute. So this is not 16 minus x to the fourth. If I were to do this by hand, I would in fact have to distribute. So I'd have to do 4 minus x squared times 4 minus x squared in order to solve this by hand. But you could also enter this into your calculator. It's mostly about the setup of the problem. So here, this is an example of when we're rotating around a horizontal line, but that horizontal line is not the x-axis. So when we rotate around a different line, there's going to be a different bottom function than 0. So in this case, the bottom function was -3.